Okay, so let's kind of catch up real quickly to where we were, because we were talking about probability. And these are all the definitions that are on the front page of your notes, because you're trying to identify these terms. Probability experiment is an action or trial through which you get specific results, okay? And they can be a lot of different things. We talked about outcome is the result of a single trial, but the sample space would include all the possible outcomes you could have in a probability experiment, okay? And the last one was sometimes you may be asked to find the probability of an event occurring, and an event can consist of one or more outcomes. So the example that they gave us, which you see on the next slide, is an event might be when I roll a die if the die is even, because there's more than one side on the die that would have an even number. If we talked about the experiment, that's just the fact that I'm rolling the die, okay? My outcome might be when I roll, I get a 3, all right? Because only one side is going to be facing up when I roll that die, and then my sample space includes everything that's possible on that die. All right, so far so good? Now, when we talked about this one, tossing a coin and then rolling a 6-sided die, we drew kind of a tree diagram to show the sample space, didn't we? Because what we found was when you toss a coin, what is it that can happen? You would either get what? Heads, or you would get tails. And when I toss that coin, does it have any bearing on what happens when I roll the die? No. So if I toss the coin, I had 2 possible ways that it could end up. I'm either going to get heads or I'm going to get tails. If I roll the die, how many possible outcomes do I have? 2. I'm rolling the die. There's 6 because it's a 6-sided die. Now, I want to see if you guys remember this. When we drew out that tree diagram, how many different outcomes did we have? 12. Because if you roll a head, then you got 6 options on what you get on the, or if, I'm sorry, if you flip and you get a head, then you have 6 options on what you get when you roll the die. And then the same thing on tails, you have 6 options there. That adds up to be 12. Now, would there have been a quick way to figure out how many possible outcomes we have without drawing the tree diagram? Multiplying. That is called the fundamental counting principle, and it is very useful. We're going to talk about it more in a minute. Now, if you have a simple event, that means that there is a single outcome. Like, for example, on that problem we just talked about, we were listing the sample space. There were 12 different things that could happen. But suppose I wanted to calculate the probability of tossing a heads and rolling a 3. There's only one way that happens out of the list of 12 outcomes, right? So that makes it a simple event because there's only one way it happens. But if there's more than one outcome, it's not a simple event, because maybe I'm wanting to know what's the probability of tossing a heads and rolling an even number. Is there more than one even number on the die? Yes, there is. So it could be a heads with a 2, a heads with a 4, a heads with a 6. Since I got more than one outcome that would meet this event, it's not simple. Does that make sense? Okay, so let's see if you can tell me whether this is simple or not. You roll a 6-sided die, and your event is that you roll at least a 4. Okay, I'm seeing some heads shake no, and I heard a few kind of quiet, not simple. So why would you say it's not simple? If it's at least a 4, what would a roll be that would fit this criteria? A 4, a 5, or a 6. There's 3 different things I could roll that would be this event. So that's why it is not simple. All right, here's that fundamental counting principle. if an event can occur in some certain number of ways, they're using the letter M to represent that, and some other event can occur in N ways, then the number of ways these two could occur in sequence, in other words, together, is M times N. Look at what we have on the board when we talked about flipping the coin and rolling the die. There were 2 outcomes on flipping the coin, 6 for rolling the die. All we had to do is multiply them together to know how many different possible outcomes there are, right? Much easier, much easier. Now, can I do it for more than 2 events? What if I wanted to flip a coin, roll a die, and spin a spinner? I could still multiply them all together. So I can have more than 2 events and just multiply them together. All right, let's see if you guys can figure this one out. If you're going to purchase a car, and I think, did we get this far last time? No, okay. So if you're going to purchase a car, let's say you work for a company and they're going to let you get a company car. That'd be pretty cool. But they've got restrictions on what your company car can be. So you have 3 manufacturers you can choose from. It's either got to be a Ford, a GM, or a Honda. And it's going to be a compact or a mid-size. And then they only give you these color options. It can be white, red, black, or green. Sorry, if you want a yellow car, you're out of luck. All right. Now, how many different ways could you select one manufacturer, one car size, and one color? So talk to me about this for a second, okay? What I think I will do is switch over here so that we can talk about this together. Okay. All right, so here's your problem. And this is what I would consider doing, okay? If you're using the fundamental counting principle, as opposed to drawing a tree diagram, which I don't know that many of us would want to draw a tree diagram, I put blanks for every choice I have to make. So how many different choices am I having to make to pick out the car? I've got 3 different things I choose. So I've got to choose the manufacturer, I've got to choose the car size, and I've got to choose the car color. So I put down 3 blanks when I do this. How many choices are there for the manufacturer?
3.
3, because it could be a Ford, a GM, or a Honda. How many choices do I have on the size?
2.
2. And the color?
4.
Okay, and then we do what with all these numbers?
Multiply.
You got it. We're going to multiply them together. And Daniel, you told me just a minute ago, I have how many different ways I can get one of these?
24.
24. That's it. That's all you would have to do. Okay? Now, that's the tree diagram. Anybody want to make one of those to figure this out? I'm sorry, what? Little b? What do you mean little? Oh. Okay. You can draw a tree diagram, but there's a lot of things that drawing the tree diagram would not be a good idea. It confirms for us, though, that using the counting principle works. Now, let's talk about types of probability. How many of you guys have actually studied probability before? Is this kind of familiar, or is this something you don't really do much? Okay, some of you have had a little bit. Some of you may remember more as we talk about this. So we're going to, usually when you talk about probability, I think most of us think of classical or theoretical probability first. And that's the idea of if Daniel came up here and tossed a coin, what do you think is the probability he would get heads? 1 out of 2, right? Because when we calculate with theoretical or classical probability, then we know that each outcome is equally likely. As long as it's a fair coin, shouldn't I have the same likelihood of getting heads as I would tails? exactly. So what we do is we would put the number of ways that what we're wanting to have occur, that would be in our numerator, over the total number of outcomes that could happen. So when we're talking about flipping the coin, and I say, what's the probability of getting heads? How many heads do you have on a coin? One. Out of how many different things can you get when you flip a coin? Two, either heads or tails. So that's why the probability would be 1/2. Okay, now let's see. These are all classical probabilities. These are things you can compute numerically because they all have an equal chance of occurring. So, because if we're rolling a 6-sided die, wouldn't you say that as long as it's been constructed correctly, you've got an equal chance of any side showing up when you roll it? So tell me, what's the probability of rolling a 3?
1 out of 6.
Because only one side is a 3 out of 6 on the die. How about event B, rolling a 7? Okay, Daniel, you're quick with 0 out of 7. Can you tell us why?
You can't roll a 7.
Because there is no 7 on the, you're exactly right. If it's impossible, that means you've got a 0% chance, 0 probability of it happening. In fact, that's really important. You need to make sure you realize that. Okay, event C, rolling a number less than 5. All right, got to figure out, some of you guys are just really Johnny on the spot today. So if you roll a number less than 5, tell me which numbers on the dice are less than 5. 1, 2, 3, 4. That's 4 sides out of 6, which you're right, we would reduce down to 2/3. And this is what it would look like. Now they're putting the decimal approximations on here because probably in the computer, it's going to ask you to go ahead and put them in. Technically, the fraction is more accurate.
Is that what you're going to add for the price on the test?
If I tell you to round to the nearest whatever, then you're going to get the decimal approximation. But I would tell you this, I would write down the fraction first because that shows me how you got it. Okay, I want to see the fraction first, and then if you're supposed to approximate it, you can. But I would reduce 4/6 down to 2/3 because that would be the simplest form of the fraction. And the fraction is more accurate than the rounded decimal value. Okay, so that's classical or theoretical probability. What did we say? In order for that to be true, we have to have what? Equally likely outcomes. Now, the second type is empirical or statistical probability. And these come from probability experiments. And then we record or observe the outcomes, collect data on it. Okay? So what we're actually doing on this is we're tallying up the relative frequency of an event. How often does something occur? So I think we may have touched on this last time. If Daniel was up here flipping that coin, because I said, we need you to flip this 100 times, is it absolutely positively guaranteed that 50 times out of 100 he gets heads? No. Each individual toss, the probability is 1/2 or 50% of getting heads and 50% for getting tails, but there's nothing that means if I flip it 3 times in a row, I can't get 3 tails in a row. I can, but is it likely that's going to happen? Not very likely. Would it be likely that I could flip the coin 20 times and get heads every time? That is very unlikely, and I can calculate that. But if I actually do the probability experiment, then I'll be able to calculate how many times did it really occur out of 100. Now, so you take your total frequency of the event to be, or the total frequency of how many times you do the experiment is your denominator, and then whatever event you're wanting to have happen, how many times that occurs is your numerator. So, and we're going to talk a little bit more about that in a minute when we look at the law of large numbers. But right now, I'm giving you a survey. These are the results that came from a telephone survey. And this is the dumbest question I think I've ever seen. What is your overall impression of the past decade, the 2000s? Okay. Whatever. How do you answer that? and basically they just want to know, did you have a positive feeling about the 2000s, year 2000 to 2009? Was it negative? Was it neither? It was just there. Or I don't know and I don't care. All right? So these are all the responses that were given. Now, here's the question. What's the probability that the next person surveyed is going to say, yeah, I've got an overall positive impression of the 2000s? Well, all we'd have to do, looking at the table, is put what in the numerator, because that's how many people so far have said positive out of 1504. Does that make sense? I would think so. You guys, I'm sure that part is not terribly confusing. So if I construct this probability correctly, 406 divided by 1504 is about 27%. So far, about 27% of the time, somebody has said, yeah, I think it's pretty positive. I feel good about it. And I could ask that question for any of the other things. If I wanted to know how many people don't know, how would you put that together? That'd be 30 over 1504. Fortunately, that's a small percentage, okay? Oh, I don't know. I was sleeping through the 2000s. I'm not sure. Okay, this is the law of large numbers that I mentioned. If an experiment is repeated over and over, the empirical probability of an event will approach the theoretical probability of the event. So this is where Daniel and the coin toss comes in, because if I gave him a coin and he only tossed it 4 times, okay, do you think that it's got to be pretty close to 2 heads, 2 tails? Or actually, does it have to end up 2 heads, 2 tails?
No.
Not at all. It could be a lot of different things. And it's all going to depend on what happens on those individual tosses. I mean, it could be 4 heads. It could be 4 tails. It could be 2 and 2. It could be anything. But if all we did is put Daniel up here for a whole day, and he tossed the coin 1,000 times, not just 100, but 1,000 times, do you think over the course of the day, it would probably get pretty close to 50% of the time it gets heads? Yeah. The answer is yes. Now, we can put him to the test if you guys think that's a good idea.
You got a coin?
Yeah, I don't know. Yeah. And here's why. I mean, think about it this way.
Is that your video thing?
That is not my penny. I don't, yeah, they went to a lot of trouble to get these pennies to look really nice and a little.
I think, yeah, they took a picture of it.
Yeah, they took a picture of it. But hang on, guys. Here's what I want you to realize. All right? Think about, how many of you got a flu shot? Not everybody did. Okay. Did anybody get a flu shot and yet you still got the flu? All right. Now, do you guys know how they come up with the vaccine that they put in that flu shot? Well, all right, here's the deal. Hang on. Those of you who had the flu, did they tell you, was it type A or type B? Did you ask?
No.
Okay. Have you heard that there's a type A and a type B? Okay, and which one's worse this year? Which one's worse, do you know? It's A. Type A is the one, it's like an H3N1 or something, a type A, that specific strain. Now, do you hear kind of what I'm saying? Is there more than one virus that's causing the flu? There are multiple strains of the flu. So when they get ready to put that flu shot together, obviously they got to do it in advance. How do they come up with what goes in the shot? They make a guess, don't they? What they think is going to be the most common strain of flu and vaccinate people against that. Now, if you've watched the news, they've given you reasons as to why it hasn't been very effective this year. What's one of them? Well, for one thing, if you're guessing, you could miss it.
Doesn't it keep changing?
And the second reason they give is that because it's a virus, it mutates quickly. And yes, this is a particularly aggressive strain this year. So, yeah.
It was bad.
Yeah, I'm hearing from, well, some of the reports I've seen on the news are just horrifying how awful it has been for some people. Exactly. I know, it's scary stuff, so you guys be careful, but listen carefully. Hang on. Shh. If you are a drug manufacturer, and let's say you've come up with, no, not a drug dealer, a drug manufacturer, and let's say you think you have come up with a cure for lung cancer, and so you go to the FDA and you say, you need to approve this drug because I've got the cure for lung cancer. And they say, really? So show us your study. And you say, well, I gave it to 2 people and they both are cured.
Wait,
What's the problem with that?
it's not enough.
Okay, because wouldn't you think you need to have a study to show that when a large number of people are involved, this is the result that's coming out. That's not enough for you to know. And the principle's the same with this. If you repeat an experiment enough, you repeat it a large enough number of times, it will level off at what the actual or the theoretical probability is. Yes, ma'am.
Isn't it really needed to get like a drug approved by the FDA? It only has to be like a certain number of people, but they don't get like a time frame. Like it could be over the course of like a long time.
It's pretty rigid to get it through. That's one reason why we have people in this country who go to other countries to get, like a lot of people will go to Mexico to get experimental drugs and things because they don't go through the same approval process and it takes a long time. They may be a little more lenient on the experimental drugs to get some data, but it hasn't been approved through the FDA. Okay, now, here's one, listen, shh, here's one more type of probability. And this kind of fits in a little bit with our discussion about flu. Subjective probability, based on intuition, educated guess, or estimates, okay? So, for example, hopefully this never happens to you, but maybe at some point in time you've got a loved one in the hospital. Maybe they had a terrible accident or they're very, very sick, and odds are pretty good at some point you're going to want to say, so doctor, what's the chance of survival? Or what's the chance that he's going to be normal if he does survive? And they're going to give you some sort of figure, like 90%. Is that what's that based on? Okay, his experience in maybe treating cases similar to that. Is that something that's hard and fast, or are there other things that maybe he's had a bunch of people who didn't survive, but maybe they were older and overweight and they had other problems, and maybe your loved one is young and healthy and strong and didn't have any other issues before this happened.
But they're a chain smoker.
Well, I'm just saying there's a lot of factors that would come into this, and ultimately it's an educated guess, right?
Right.
I mean, there's nothing statistically that you could look at that would give you it has to be this percent. All right, somewhere somebody's making an objective call. All right, guys, see if you can tell me this. Which type of probability? We've got 3. Do you remember what they're called? What's the first one? Classical. That's the one that everything has an equally likely outcome. What's the second one we talked about? Empirical or statistical, and that's where it's based off of doing an experiment over and over. And the third one we just said was subjective. So tell me about this. The probability you get the flu this year is 0.1. First of all, that seems really low compared to how it turned out this year. But Daniel says subjective. Do y'all agree with that? What do you think? Is that subjective?
She's shaking her head no.
I'm asking, is that subjective? Okay, well, let me ask you this. If it is classical, it means that you've got an equally likely chance of either event happening, getting the flu or not getting the flu. Do you think this sounds like that's equally likely?
No.
Because they're always
different.
Yeah, they're always telling you you've got certain people that are high risk versus others. So that's not an equally likely chance of getting the flu. So let's throw that one out. So that would leave us with either empirical, which means this is based on doing experiments over and over and over, or subjective. What do y'all think?
Subjective.
I believe this has to be subjective, right? Because this is based on somebody. Now, there may be some research that they've looked at that's helped them make a guess, but there's nothing hard and fast that would say it has to be 0.1. Okay? What about this one? The probability that a voter chosen at random would be younger than 35 years old is 0.3. What would you say on that? If you pick a voter at random, what's the probability? Or the probability is 0.3 that they're 35 years old. What kind of probability do you think that is? We're thinking, aren't we? Okay, I'm hearing several people say empirical. Can you tell me why? Because it's not an answer.
I say classical. Ooh, let's go.
Okay, tell me why.
I say it's classical because it's at random, and like everybody has like the chance of it being like them being 35 years old. I think we should never know. So I think
Hold on.
to that certain amount of people.
Hold on. How do you think they would come up with a probability like this? Say that again, Brooklyn. Ooh, okay, listen to what Brooklyn just said. She said past experience, like if you looked at voting records from earlier years, you could probably figure out about what percent in this age group tended to vote. That's a good idea, because you also do like a survey, maybe contact voters ahead of time, potential voters, to find out who's planning to vote, and then see what ages they are. What does that sound like? Does that sound like classical, or does that sound like empirical? Good. All right. It's an empirical probability. You've looked at some data, but it's not something that you can calculate because it's equally likely to happen. Now, what about this one? The probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. That's classical. If every ticket has an equal chance of being drawn, right? As long as it's in the bucket when they draw. So that's classical. Okay. Just like we reviewed a minute ago, that our R values had to be between -1 and +1, we've also got a rule about our probabilities. And this says that your probability of any event happening has to be between what two numbers? 0 and 1. Now, if the probability of something happening is 0, what does that mean? It is not going to happen. Guaranteed not going to happen. Sort of like rolling a 7 when you roll a 6-sided die. What does it mean if the probability is 1?
It's going to happen.
Because it's 100%. Remember, 1 as a decimal number, if you turn it into a percent, is 100%. So it's guaranteed, no way it can't happen. It's for sure going to happen, okay? So it's got to be a decimal number between 0 and 1 if it's written in decimal form. And this would give you sort of a visual idea of what it would look like spread out on a scale. All right. Do you guys know what it means to have a complement of something else? And that's not with an I where somebody said something nice to you. This is complementary with an E. Like, for example, do you remember anything about complementary angles?
Yes.
Maybe from geometry?
Yeah.
So if I had an angle that's 30 degrees,
60.
how much would an angle be that's complementary?
60.
60, because what did it mean?
90.
If I added those two together, I got 90, okay?
Supplementary.
And supplementary is 180. Now, here's the idea. Hang on a second. If I were to add an angle with its complement, I get the whole 90 degrees, right? Okay. So if I'm talking about complementary events, what it means is the complement, and we're going to denote it with this little apostrophe, they call it prime. So E prime means not this event. This would maybe be the event I'm looking to have happen. So either the event happens or This would be all the ways the event wouldn't happen. But guess what I have if I put the two together? The whole sample space. Everything that could happen is going to be included between the event and the complement of its event. Does that make sense?
Sort of.
The two together has to cover everything that could happen. It's sort of like if I flip a coin and the event I want is heads, where would heads be? In the red circle or in the tan box?
The red circle.
The red circle, that's getting ahead. If I don't get ahead, I got a what? A tail. That's out here. Would the two together be everything that can happen when I flip the coin? Yes, it would.
So
That's
maybe
going
the complement.
So the complement added to the event will have to equal everything that could happen. Every time. Okay? So we said, we call it E prime. And these will be some little basic formulas that might help us in a little bit. The probability of an event plus the probability of the complement has to equal 1, because remember, that's everything. It includes everything. Now, I can rearrange this so that if I needed to find the probability of the event, I could do 1 minus the probability of the complement, or 1 minus the probability of the event would give me the probability of the complement. All right, so now let's look at something that's not as abstract. Let's see if you guys can figure this out. This is a survey from 1,000 employees at a company, and their ages have been recorded, and we've kept up with the frequency. How many people fell in each of these age brackets? You're asked to find the probability that if you randomly choose an employee, that employee is not between 25 and 34 years old. Now, how many of you, just by show of hands, say, I can figure that out? Okay. How many of you say, well, I can figure it out, and I can think of more than one way to figure it out? All right, I'm still seeing a few hands. So, Tamari, tell me what you would do to figure out the probability if I randomly choose an employee, they're not between 25 and 34 years old. Are y'all following what he just said? Yeah, okay. Now, let me show you here. I'm going to flip back over to this so we can look at it on the paper. And here's what I just heard you say. You said you would get the probability, where were we? Right here. That you would get the probability that somebody was between 25 and 34. And that's what? Looks like 366 out of 1,000. If I made that into a decimal number, that's 0.366, right? Well, let's just leave it as 0.366 right now. So then you said you would do what to get the probability that they're not in that group? Subtract it from 1. That's giving us the complement. So 1 minus the probability of that event is 1 minus 0.366, which is how much? 6.34, isn't it?
Yes.
Okay. He used the complement. What's the long way of getting it? Add up all the others and then put it over 1,000. Can you do it either way? Absolutely. But sometimes the complement is a shortcut if you understand what that means. Does that make sense? Okay. Fortunately, they were nice enough to give us 1,000 in the sample because that made it easy to calculate. So this is, they do it the same way Tamarian did. We found the probability in that group, subtracted it from 1, and we got 0.634, about 63%, a little over 63%.
But on the test, you can put the fraction of the decimal.
I will give you an instruction about how to write it. My advice is write it down in the fraction form because you're going to, I mean, if you get it as a decimal, you put it in your calculator as a fraction, right? You would type in 634 divided by 1,000 in order to know that it's 0.634. So write it in fraction form, and then if you put equals to decimal, they're both there and you're safe. Okay? All right, look at this. We got a spinner. And we're going to figure out the probability of tossing a coin and spinning the spinner to see what would be the probability of tossing a tail and spinning an odd number. Now, we talked about the fundamental counting principle. Can anybody tell me what you think are going to be the total number of possible outcomes?
16.
Okay, I hear 16. Where's that coming from, Daniel?
Because you have two,
You toss a coin, there's two things that can happen. And if I look at the spinner, there are how many different numbers I could get? 8. And so 2 times 8 is 16. Is everybody good with that? We got 16 possible outcomes here. We want to know what's the probability that we toss a tail and spin an odd number. Now, it says use a tree diagram. We can do that. Can you figure out a way to get it without the tree diagram?
Yeah, I mean, numbers are on that.
Okay, so I've got to have a tail and an odd number. So if I get a tail, how many odd numbers can go with it? There's 4. I've got a 1, a 3, a 5, and a 7. Wouldn't that mean there are 4 different ways to get a tail and an odd number out of those 16? That's how I do it without the tree diagram. Now I'm going to show you. If you wanted to make the tree diagram, that's what it looks like. But I could still go through and count up how many of those are tailed with an odd number. It's 4 out of 16, which reduces to 1/4 or 25%. Okay? Give me a quick signal. Are we thumbs up, thumbs down, or somewhere in the middle? How are we doing? Okay, I'm seeing several thumbs up. That's good. Here's an example of one you don't want a tree diagram for. Your college ID number has 8 digits in it. And you can use each digit 0 through 9, and you can repeat digits. So in other words, if you wanted 9999999 to be your college ID, that's possible. Not that you get to choose, but it's possible that one could come out. What would be the probability of getting your college ID number if you randomly generate 8 digits? How do we figure that out? So go ahead. What were you going to say? You're thinking about a factorial. We're going to talk about that soon. Not quite yet, though. And factorial is a little bit different. So here's what I would do, guys. Is this, now tell me something, is this a good candidate for the fundamental counting principle? What do you say?
Yes.
All right, and that's because I've got to make choices for how many digits? Well, no, well, I mean, how many digits are in the number? 8. So if I draw 1, 2, 3, 4, 5, 6, 7, 8 blanks, you're going to tell me how many different options I have for choosing the first number. What do you say? Because the number 0 through 9, that's 10 different digits, isn't it? Now, did it say I could repeat? Yes, it did. So how many options do I have for the next digit? Oh my. Is every one of these going to be 10?
Yes.
Now, what Daniel was mentioning a minute ago when he talked about the exclamation point, it's called a factorial. That's when you start at a number and you count down to 1 and you're multiplying. It's a shortcut way of saying, and that would have been if they told us we couldn't repeat numbers. Because if I had 10 numbers that I'm choosing from and I pick one here, but it says you can't repeat numbers, that only leaves how many to choose for the next one? 9, because I can't use the one I've already used. Now I've used 2 of them, so how many would I have here? 8. So we'll be talking about that eventually. This one said we could repeat. And what do I do to find out how many possible combinations of digits we end up with? Oh my gosh, that's 10 to the 8th power, which is 100 million, isn't it? That's a 1 with 8 zeros after it. Now, is that my answer? Is that my answer? What did the question say to find? Yes, what's the probability that you randomly get your college ID number? How many of these numbers match yours? Oh my goodness. That is not a likely event, is it? Think about this before you end up deciding to buy a lottery ticket one day, all right? Not a likely event to occur.
But you never know.
Well, you never know. You can choose to play the game, but you want to be smart about it and look at what the odds are before you do it, the probability. Now, that's everything that's in 3.1. You guys picked up your notes on 3.2, correct? Okay, so let's see if we can get through this. One of the reasons I wanted to try to do this if we can, I had some students let me know that week before spring break, some of you are going to be gone on that Thursday, correct? If it's possible that we can comfortably get through this material by the end of next week, what if we were to test on that Tuesday before spring break and then just not have class on that Thursday? Would that work?
Just not have class that day.
And just not have class that Thursday. You start spring break a little early, maybe. Okay, since some of you are going to be gone, we may try to do that. Now, conditional probability. All right. Conditional probability is when you find the probability of an event occurring given that some other event has already occurred. Okay, and typically we have to be aware of this when the first event changes the likelihood of the second event occurring. Okay, for example, if I had you guys ever like reach in your drawer without the light on, just pull out a couple of socks, you pay no attention?
No.
Okay, let's say you just reach in, you randomly grab 2 socks out of the drawer, all right, and you're wondering if they're gonna match. So let's say the first one you grab is a black sock, okay, and you started off with 3 black socks and 3 white socks, nothing paired up before you started, all right? So if you reach in and you get a black sock, what was the probability that you were going to get a black sock the first time you drew one out? Well, it would be 3 out of 6, which is 1 out of 2, right? But now, if I've already got a black sock in my hand and I go back to draw the next time, what's my exactly, that probability changed, didn't it? Because the outcome of the first event affected the outcome of the second event. All right, now, symbolically, this is what it looks like when we're talking about the probability of some event given that another event has occurred. You're going to see the P in front standing for probability of event B occurring given that vertical line means given that A has already occurred. Okay, and we'll look at some examples of this. Here's the first one. Let's say, okay, and this is where you guys tend to maybe need a little help. I was telling my class last night, back when I was younger and there was no cell phones, there was no computer, there were no video games, guess what a lot of times you ended up doing for recreation or for fun? You played cards, okay? You played spades, you played hearts, you played cards. So we knew the questions like this are designed for people more of my generation because we were very familiar with cards. How many of you guys know how many cards are in a full deck? Very good. Do you know how many suits are in a full deck? There are 4. What are they called?
Ace.
Okay, the suits are, hang on, spades, diamonds, hearts, and clubs. Now, listen, out of those 4 suits, how many of them are black? 2. How many are red? 2. How many cards are in each suit? 13. 52 divided by 4 is 13. Now, here's another question. what is a face card? Because sometimes they'll talk about face cards.
King, a queen, or
Jack.
A king, a queen, or a jack. Don't count an ace that doesn't have a face on it. They're face cards because they actually have faces of people on them, okay? Now, make sure you know some basic facts about cards because in probability, that's a lot of times what they use. All right, listen. 2 cards are selected in sequence from a standard deck. You want the probability that the second card is a queen, given that the first card is a king, okay? Now, and that says assume that the king is not replaced. In other words, it's still in your hand. Now, do you know how to calculate this? What would you do?
No.
Okay, now it didn't ask for this, but I know that the first card was a king. Okay, what was the probability that out of a standard deck of cards I would draw a king?
4 out of 52.
Exactly. There are 4 kings out of 52 in that deck. Now that's not what it asked me for, but it asked me if that first card is a king, what's the probability that the next card I draw is a queen?
4 out of 51.
There you go. There are still 4 queens in there, but I'm not starting with 52 cards anymore. One's been pulled out, and it's 51. That's my answer. Okay? So make sure you understand that that first event changed the probability on the second event. Because if I was working with a full deck, it would have been 4 out of 52.
No, like, what if we didn't know that? Like, how many cards were in there?
You better learn it.
better learn.
Man, no, I'm saying, like, what if there was, like, on the test or whatever? Like, there won't be any questions like that, like, where you just have to know.
Yeah.
But I'm saying, like, prior to that, like, what if somebody didn't know that?
That's why I'm telling you now.
I got you.
Okay. So it's up to you to make sure you know it. And if you wanted to turn that into a decimal, because sometimes that may be easier to recognize, that's less than 8%. Is that something if you went to Vegas, you would put your money on, ooh, I bet I'm going to get a queen on this card if I draw it. Yeah, you need to be careful if you're going to bet on it. Okay. Now this is really important. And this sometimes trips up students in terms of how to read this. Look what they've given us. They've given us a table. What this represents is the results of a study where researchers examined a child's IQ and the presence of a specific gene in the child, okay? And we're supposed to find the probability that a child has a high IQ given that the child has the gene, okay? Now, do you have any idea what that means in terms of how we're going to figure this thing out? What'd you say? Well, let's look at what this is actually asking us to find. We're going to find the probability that a child has a high IQ given that the child has the gene or that the gene is present. Now, this is a little bit different from the one we just did simply because we're given this table and look how it's set up. You have columns that give you whether the gene is present, whether the gene is not present, and then you've got totals. Your rows are high IQ, normal IQ, and then totals. Now, here's what I'm going to tell you. If you see that it has given that in there, that's telling you you're only going to use one row or one column. Now, you tell me, do I need a row or do I need a column here? What am I going to narrow things down to?
I mean a column.
A column, because what does it tell me given that what? The gene is present. I am only interested in the people where the gene was present because it said find the probability that they have a high IQ given the gene is present. So how many of these students have the gene?
72.
this number right here. That's my denominator. Those are the only ones I'm interested in out of this group. I do not use this number because this includes people who didn't have the gene, okay? Now, out of those 72 that had the gene, how many have a high IQ? And then I could reduce that down, put it in decimal form or whatever, and that's how I would calculate it. Does that sound simple? Yeah. Will you remember to do it? I hope so. Okay, so if you look at this, it's basically telling you the only thing you want to look at is that column where the gene is present. Then you pick out for the numerator the ones that have the high IQ. This makes it about 46%, okay, if you actually divide that out. All right, let's talk for a second about the difference between independent events and dependent. If they're independent, what happens on the first event does not affect the outcome of the second. Think about the ones we looked at the beginning where we talked about tossing a coin and rolling a die. Does the coin toss affect what happens when you roll it all? No. Those are totally independent, right? Okay. And what this is saying is if you have the probability of event B occurring, given that A has occurred, does that make any difference in what B is? No. It's if they're independent, then you're going to end up with it being the same no matter whether A occurred or not. Now, when they're dependent, that changes what the probability is on the second event. So let's decide if these are independent or dependent. Selecting a king from a standard deck, not replacing it, and then getting a queen. That's what we talked about a minute ago. Are those independent or are they dependent? Does what happens on the first draw affect the probability of the second one? Those are dependent, right? There you go. All right, look at this one. Tossing a coin, getting a head, then rolling a six-sided die and getting a 6. Are those independent or dependent? Okay, I'm having a hard time telling if you're saying independent or dependent. How many of you, raise your hand if you say these are independent? How many of you say these are dependent? Good job. These are independent because it doesn't matter what happens on tossing the coin. It's not going to affect rolling the die. Now, here's where the multiplication rule comes in for us, because sort of like when we use that counting principle to figure out how many ways could something happen when we had two different events, that comes from this, the multiplication rule. And it says, not only can I use the counting principle to count up how many ways something can happen, but I can actually compute the probabilities. If I want to know what the probability of both of those things occurring is, I can take the probability of A and then I'll multiply it times the probability of B occurring given that A has occurred. Okay? Now, if they're dependent, then that means I got to be really careful because this is not the same thing as the probability of B. Okay? What if they're independent though? Then it's just the probability of A times the probability of B. Does that make sense? Because as long as they're independent, it didn't matter what happened on the first thing. It's still going to be the same probability for the second event. Okay? It didn't change. And I can do it for multiple things that I'm trying to choose. So I think we'll probably go through, let's see, how much more do we have? We probably are going to be just a little bit short of having time to finish the notes in here, but I think it'll be okay because we can pick up with that next time. So 2 cards are selected without replacing the first card from a standard deck. Can you get the probability of selecting a king and then selecting a queen? We already did the preliminary work for that on the very first thing on this set of notes. Because what was the probability that out of a complete deck of cards, I draw a king? 4 out of 52. If I'm holding the king in my hand, because it says I'm not going to replace it, what's the probability the next card was a queen? And what am I supposed to do with those 2 probabilities? If it says find the probability of selecting a king and then selecting a queen. multiply. Remember, this is the multiplication rule. Anytime you see and, it means multiply. Okay? So if I want the probability of this and this happening, multiply those together. So what do you get if you multiply 4 over 52 times 4 over 51? A little tiny number. Is that very likely to occur? No, it is not. You have less than 1% likelihood that this would occur. Okay? Look at this one. A coin is tossed and a die is rolled. Can you find the probability of getting a head and then rolling a 6? What would you tell me is the probability of getting a head? 1 out of 2. What's the probability of rolling a 6? 1 out of 6. So what's the probability both these things happen? Because I multiply 1/2 times 1/6, and I get 1 out of 12, which is a little over 8%. Okay? And this one I think is probably a good place for us to pick up next time. So I'm going to stop here.